Let's discuss something we mentioned last time, but we couldn't understand. I mentioned a statement, and I said it was true, but I didn't know why. No one else did either. So let's discuss it today. There was a statement about almost complex structures compatible with the symplectic form, and more precisely, an almost complex structure is compatible with the metric and the symplectic form if and only if we have this equality. And the question is is the space of such almost complex structures homotype equivalent to a point. More precisely, I want to fix the form, the symplectic form, but I don't want to fix the metric. So almost complex structures R to N compatible with omega and some metric. The metric is determined by J, and vice versa. If we have an almost complex structure, then we get at most one metric which satisfies this formula, and Well, the question is um, um, how to understand the space of such almost complex structures. Now, my claim is the space of almost complex structures with this property is homology equivalent to the space of metrics. R2n. It's 2n everywhere. Okay. Now the easy part. The space of all metrics is contractible. Is this clear to everyone?
Can you repeat the statement?
The space of all metrics, meaning the space of all bilinear symmetric forms, non-degenerate, positive definite, on R2n, and in fact on Rm for arbitrary m, is contractible.
Oh, it's not immediately clear.
Well, the key observation is that this the space is a convex subset of the space of all symmetric bilinear forms, which is a vector space, and basically, by definition, if we take any positive definite symmetric bilinear form and another positive definite symmetric bilinear form, then for every t between 0 and 1, the linear combination is again positive definite symmetric bilinear. And, well, basically this follows from the fact that positive real numbers form a convex subset of all real numbers.
What is the homology and the jet? I mean, you're using the jet angles and
almost complex structures is the space of almost complex structures has a topology which is induced from the space of matrices. And
there's some sections of
no. We consider only the fiber over a point. So almost complex structures in this definition is a subset of the set of all linear maps from R to N to R to N.
So it's important that
It's
you're
time
using
space.
If it was not R2, it was any manifold,
Well, yes. Then after we understand the fiber, if we manage to prove that the fiber is contractible, then the space of sections will be contractible as well. Okay, so this part is straightforward. Now. My claim is that these two spaces are homotopy equivalent, although they're not the same. Let me construct a deformation retraction from the space of all metrics to the space of almost complex structures. Do the words deformation, retraction make sense? Okay. Well, okay, let's see. So we fix omega. Let's take an arbitrary metric. And let's define a linear map from R to N. Such that we have this formula for all x and y inside R to N. Why does such a linear map exist? Well, if, for example, if I fix if I fix if I fix one of the variables, let's say x, and look at the right hand side, I get a linear function of y. But every linear function of y is given by taking the scalar product with some element of R to n. Well, I call this element a of x. And then one can check that this is the resulting map is well defined and linear. But it's not just linear. It's also anti-symmetric. Well, now I will need to erase something because the blackboard is small. Anti-symmetric with respect to the scalar product. What does this mean? Well, this means AXY is X minus XAY for all XY inside R to N. Okay, why is this true? Well, because omega is antisymmetric. What does this mean? Well, this thing is the same as AYX, and this is the same as omega YX, and this is the same as minus omega XY. Okay. And now, does this make any sense? Now we need to remember a statement from linear algebra over the real numbers, which says that every normal well, suppose we have some Euclidean space, then every normal map is sort of diagonalizable with respect to some orthogonal basis of R to N. Well, sort of diagonalizable means that well, over the reals, not all matrices are diagonalizable, but the worst that could happen are blocks of the form AB minus BA. Now, does this statement sound familiar? Okay. Let's see what this. If it doesn't sound familiar, it's it's easy enough to look it up somewhere. If you Google search for diagonalization, normal operators, you'll probably find quite a lot of references with proofs. So, and by the way, what is a normal operator? Они знают лучше, но вот я поэтому вот я хочу, значит, вот я знаю хуже, вот я хочу знать. What is a normal operator? Well, a normal operator is an operator which commutes with its conjugate operator, and well, which is why this notion depends on the metric. Okay. Well, anti-symmetric operators clearly commute with the conjugate operators. In particular, well.
Symmetric operator.
So do symmetric operators and orthogonal operators, and in the complex case, unitary operators, and so on. Okay. Now we have an anti-symmetric operator. Well, an anti-symmetric operator and in the anti-symmetric case, there exists a basis for every anti-symmetric operator. There exists a basis in which this operator is block diagonal with blocks of the form 0a minus a0. Well, a can't be 0 because capital A is non-degenerate. So 0 is not an eigenvalue. Okay, now My claim is it's clear from this formula that the square of A is not necessarily minus the identity. The square of a block like this one is minus A squared times the identity. Okay, but it's clear that a matrix such as this one can be joined with either 0, 1, minus 1, 0, or 0, minus 1, 1, 0, depending on the sign of A. And another observation is we can also deform a metric. We can also deform the metric, the one we use to define A, so that the identity remains true during the deformation. Let me write this down. So there exists a family of operators and metrics such that at point at t equals 0, we have the original operator in metric, and for t equal 1, we have an operator which squares to minus 1 and some metric. And this gives a deformation retraction from the space of all metrics on Rn onto the space of metrics such that the operator A defined by AT x y V is omega xy for all xy. Okay, for all t. Yes, where was I? Yes, so not all metrics give us an almost complex structure. If we use this formula as the definition of the operator A, only some metrics do, and this family gives us let's call metrics which result in an almost complex structure good metrics. So this thing is a deformation retraction of the space of all metrics onto the space of good metrics. The space of good metrics is the same as the space of almost complex structure, because almost complex structures, well, because well, using this formula, A defines a metric and vice versa. Now, there is one thing which is not completely clear from this argument. What exactly is the deformation? Well, let's see. After all, the basis or a basis in which A orthogonalizes, diagonalizes, does not depend continuously on A. So how to construct such a family which would be continuous? Well, let's see. For every matrix or for every operator, we can take the operator times the adjoint operator, and the result would be self-adjoint. Okay, so the result would be self-adjoint, and well, let me also multiply by -1. Then I get a matrix or an operator which would be not only self-adjoint but which would have such that all eigenvalues would be positive, and Well, it's clear from this formula what this matrix what this matrix is. It's just my plus a squared times the identity. Okay, now let me take b to be the positive square root of this matrix, and well, this time my claim is that B depends continuously on A. And well, I've run out of space on the blackboard, so I'll just say the rest, but I will not write it down. So we construct the family AT by multiplying A on the left or on the right, I think it doesn't matter, by the powers of B ranging from 0, in which case we get A, to -1. In which case we get a matrix that squares to -1. And well, this time we get something which depends continuously on A. And how to check what I've just said? Well, to check it, one could use the diagonalization argument and then check the statement for each block individually. So this gives me a family of antisymmetric matrices. Antisymmetric with respect to what? With respect to some form which is uniquely determined by the matrix. So when I change the matrix, I also have to change the form. Okay, so well, the argument is not entirely straightforward, but nevertheless we get something which is contractible. It is согласен, не согласен?
Согласен.
Good.
I don't understand what happens to the metric. So it is fixed.
No. Well, first of all, we construct a family of operators, but then we need to change the metric as well. But it's determined by this formula.
Okay, so omega is fixed.
Omega is fixed, yes.
It was written.
The scalar product with respect.
No, above that. So it was. Yes.
Well, at the end.
Может, левее, там просто написано, что метрика, значит, с индексом t, да, равна вот чему-то.
Значит, yes, thank you. A. So at the moment 0, we have the original metric, and then at the last moment we get some metric. We don't know which, but some metric.
Okay. So then they're not equal.
Not necessarily.
Okay.
They're equal if and only if the original metric was good.
Очень непростое рассуждение.
Ну, непростое, может быть, потому что там я что-то не понимаю. Может, там есть какое-то простое рассуждение, но...
Нету простого же. Это относительно стандартное рассуждение многих людей я читал в 5 местах.
Вы,
И
значит,
это лучше из того, что я читал.
ну, человечество ничего не
Ну
придумало.
вот да. Ну почему-то все говорят, что это просто. По-моему, это не просто.
Ну, здесь психология. То есть обычно мы, значит,
Но все равно не просто.
обычно мы что-то большое стягиваем на что-то маленькое, и мы при этом хотим понять на что-то большое.
Да.
Вот, а здесь мы хотим понять что-то маленькое, мы на него стягиваем что-то большое. Окей.
Мне кажется, что это придумал Громов.
Громов.
Мне так кажется. Ну вот.
Anyway, well, I haven't written all the details, but I think starting from this, the rest should be just a straightforward check using the diagonal form of A. And as I've just said, in Russian, normally we want to understand something big, and we deformation retract it onto something smaller. And here we do it the other way around. We want to understand something small, and we take something bigger, which we know is contractible, and then we deformation retract the big space onto the small space again.
Like Bingo house.
Bing's house.
Bing's house.
A house with 2 rooms. Well, it's a space which is contractible, but what? But not collapsible.
It's not trivial. No, it's not trivial.
Yes, yes. Well, I vaguely remember the idea.
Remember the picture.
It's a polyhedron which is contractible, but in order to deformation retract it onto a point, one first needs to make it more complicated. That's vaguely the idea. Anyway, well, we've spent some time on this, but still, our goal is to understand everything, not to rush through. Отец, ну куда сбежал? Anyway, are there any questions? Okay. Well, let's talk a little about the symplectic action. Okay, well, last time we last time we talked a little about the symplectic action. Let's try to remember the definition. Okay, we have a symplectic manifold. So we have a symplectic form, which we call omega, and we have a family of smooth functions on M, which we assume one periodic, and this is well, this is well, this is okay. Another thing we need to assume is this: the form, the class of the form should be integral, which means every the form evaluated on every 2 cycles should be an integer, and this is I think this is it. This is all we need. Okay. Okay. Well, I've written something. Let's see. Well, first of all, let's see what it says here and whether or not it makes any sense at all. So, what is U and what is B? No, sorry. U is a map from the unit disk in C, which which is a homotopy between X and the or a constant loop. So we take a contractible loop. We can find a homotopy between this loop and a constant map. Well, there are several such homotopies. It doesn't matter which is one, and call it U. Okay, now.
Excuse me. This letter is Z or what?
Which one?
A of what?
A of X.
X.
Yes, X is an element of L naught of M, which means it's a contractible loop.
Okay. Just I
Uh,
don't understand what is the difference between U and X.
U is the
Of course, I don't understand не понимаю, что написано, где X, а где U.
Так, да, это хорошо. Значит, вот здесь X. Здесь U. Вот здесь X.
И выше еще главное, вот тут. Левее, вот тут. Выше.
В определении X.
В определении X.
Yes.
Похож на U.
Contractible loops. Okay. So this part is clear. What is this? Well, ht is a function. X of t is an element of M. We can apply. We can take the value of the function and we do this for every t. Then we integrate.
The left part, U upper side is the pullback.
Yes, we pull back omega. We get some form on B on the disk. Then we integrate along B. And this is well defined. This thing is well defined. Modulo Z, because if I choose another U, the value of the value of the second summon does not change. And the first one changes by an integer because of this assumption. Okay. Now, let me check whether or not I messed up the definition. If I did, we'll get in trouble sooner or later. Здесь уже никто не проверяет, что я пишу. Поэтому я значит сам, что и что правильно не правильно. Окей. Anyway, now we need to understand the differential of let's understand the differential of this map. Well, first of all, what is the differential? Well, the differential is is a map from the tangent space to from the tangent space to L naught to R.
Is it obvious that this L naught is a smooth manifold?
Sort of. If I take something which is well, first of all, if I take well, first of all, let's try to understand what the tangent space is, and then we'll see. Well, since we have tangent spaces, we probably have manifolds as well. But and then we'll also understand what kind of manifolds these objects are. Well, obviously they're not finite dimensional, but a manifold is locally Euclidean space. A finite dimensional manifold is locally Euclidean space. Well. Here we have something infinite dimensional. So locally it's what? Let's see. So let me take X, which is a periodic one periodic function from R to M. Let's not worry about whether or not it's contractible. Some function. One periodic. What's the tangent space to L naught M at X? Well, it's the set of all the set of all okay, well, basically we do the following thing. We take the tangent bundle of M, yeah, sorry. We take the pullback using X. We're allowed to do this, and then we take smooth sections of the resulting vector bundle over the circle, or which is the same. We take periodic sections of the corresponding vector bundle over R. More explicitly, it's more explicitly the space can be described as the set of all maps from the set of all maps psi from R to Tm, such that, well, psi T belongs to T x of Tm. So at point T, we get an element of the tangent space to M at x of T, and the family of vectors psi t should be one periodic, meaning psi t plus 1 should be psi t. Okay, now now we can see the sort of space this the sort of topological vector space which locally models this smooth manifold. It's the space of sections of some vector bundle on R. It's a topological vector space. It's not Banach, but it does have some good properties. I think it's Fréchet. Does anyone remember what a Fréchet space is? We'll need some definitions from functional analysis as well. Not today, but in a week or two. A space, a topological vector space, is Fréchet if and only if it has a translation invariant metric, and it is complete with respect to this metric. All Banach spaces are Fréchet, but the converse is not true. And but on the other hand, Fréchet spaces are not too different, topologically they're not too different from Banach spaces. For example, all Fréchet manifolds are Banach manifolds, and vice versa, obviously. If we prove that L naught is a Fréchet manifold, it will also be a Banach manifold. And moreover, it turns out that topologically we could do even better. Fréchet manifolds and Hilbert manifolds topologically are the same. So if one wishes, one.
I'm sorry, I have a question. In the very first definition of L naught, is it smooth functions or what?
Smooth, yes.
C infinity, yeah.
Yes, we don't need it. We don't need it in this. Although, we. In this definition, we only need x to be, let's say, C1 smooth. We don't need C infinity. But shortly we will need all maps to be smooth or sufficiently smooth. So let's just say everything is smooth. U, X, and so on. well, we want to pull back a differential form.
Of course, but
So we want this to be at least C1. And then we would like x also to be C1 or else. Okay. Now, so the answer is it looks plausible that L naught is indeed a manifold, and moreover a Frechet manifold with the model Frechet space being the space of sections of a smooth vector bundle on the circle of rank equal the dimension of the manifold. Well, smoothly, there are just two vector bundles over R or of any given rank. Over S1 of any given rank. So one is orientable, the other is non-orientable. Well, so this space is really well defined, meaning it doesn't really depend on M. So it looks plausible that L naught is indeed a manifold, but there could be problems with this statement, and I think some version of it is true, but I'm not sure if it is literally true. What do you think? Это кто-нибудь это проверил вообще, там, что это многообразие, там, фреши, там, тра-ля-ля? Никто не проверил.
Я просто не знаю. Ну, я знаю, что всегда старались пополнить сначала, чтобы это стало каким-то более знакомым объектом. Поэтому переходили, там P появлялось, LP, какое-то пространство сечений, дубль БП. Нам нужно...
Смотри, да, значит, это если ты хочешь Банахова. Вот, а здесь, значит, здесь...
Чего-нибудь хочется.
Нет, смотри, здесь, значит, по-моему, в каком-то смысле уже, значит, вот эта, значит, штука полна, но не относительно нормы, а относительно, там, значит, смотри, там, значит, по-моему, утверждение такое, что, я уже сам все забыл, значит, если, да, значит, здесь нету нормы, но здесь есть какое-то семейство полунорм, там производные, там максимум производных и так далее. И, значит, говорится следующее, что если, ну, в общем, да, сейчас нужно вспоминать, в общем, значит, иметь инвариантную, трансляционную инвариантную метрику, то же самое, что, в которой это будет полное. То же самое, что иметь семейство полунорм, там, может быть, с какими-то условиями, но которые здесь, значит, которые здесь вроде как выполнены. В общем, это нужно вспоминать. В общем, у меня такое ощущение, что без всяких пополнений вот эта штука будет пространством Фреше. Это не то же самое, что пространство Банаха, но, значит, следующее по сложности класса. Хорошо. В общем, человечество не озаботилось, там, видимо, выяснением ответа на этот вопрос.
И не сравнивали.
Okay. Now, well, anyway, let's pretend this space is indeed a smooth manifold, and let's calculate the differential of the action functional. Well, what does this mean? Let's see. Планируем, ну, собственно, отсюда выгонят просто. Так, во сколько у нас заканчивается первая часть?
Уже давно должна была.
Так, первая часть уже закончилась. Well, it looks like we need to have a break because other people will be asking us to vacate the room in a short while. Anyway, when I was supposed to finish, well, I think we started. We started late, but it was my fault. Anyway, let's have a break. Let's have a 20 minutes break, and then we'll meet in a room. Well, in a different room. I don't remember the exact number. Somewhere on the second floor. Okay, so our next task is to calculate the differential of the action functional.
Потому что во второй части нет звука. И вот сейчас надо все проверить, чтобы все...
Да, давайте проверим.
Да, сейчас я пока еще трансляцию с собой.
By the way, is it true that the space of almost complex structures for any manifolds is contractible? For dimension 3 it is true, but
For dimension 3 it is not true because the space is empty and the empty space is not contractible. On the other hand, in dimension 2 the space of almost complex structures is it has two components, and both are contractible, and I don't think it's true in higher dimensions.
because in dimension 3 it uses hyperbolic geometry and other things. So
Well, again, in dimension 3, the space of almost complex structures is empty.
no, in dimension 2.
Well, in dimension 2, yes. Basically, if you take the space of almost complex structures over a fixed two-dimensional manifold, it's not quite the same as the space of hyperbolic structures because well to get the latter you need to quotient out by the mapping class group. But in higher dimensions the space of almost complex structures without any further assumptions is the space of sections of the endomorphism bundle of DM such that the square is -1. And well, this the fiber this is a fiber bundle over M. The fiber has a non-trivial topology, so there's no reason to assume that the space of sections will be contractible. Okay. Well, it's okay. This is probably too much, but. Okay. So we have the hyperbolic action, no, not the hyperbolic, the symplectic action given by this formula. We want to calculate the differential of this action, meaning no, probably it's probably related to something from mechanics, but I'm not sure what exactly. Почему это действие? Okay. Okay, now we want to understand the following thing. Okay, so suppose I have suppose I have a family of loops which which gives me this tangent vector. Well, what does this mean? Well, this means This means we when we take this family and differentiate it along S at S equals 0, we get this vector. Now my claim is that when I take the action, apply it to every xs, differentiate, I get omega well, I've forgotten the formula. I'll just well, I'll write it down and then I'll explain. What the formula means, and then we'll see why the formula is true. Okay, now let's see. Omega is the same omega as in the definition of M. It's the symplectic structure. Well, x prime of t is simply the derivative of x at a point t inside 0, 1. Now, what is xt? Well, let's okay, I think this is the right notation. It's the it's the I think the correct terminology is the Hamiltonian vector field. Now, what is this field? Well, it is defined by the following formula. We take omega and substitute x as in the first place, and then we get a one form. Well, starting from a two form, we get a one form. And this should be equal dh. And this is minus. Minus or plus?
It seems to be minus. But
okay, maybe yes. There are some signs in Salomon's notes. There are some signs which don't quite match. So maybe it's because of this. Let me try. Well, in the notes it says plus.
okay.
But maybe it's an illusion. Maybe it should be minus. I don't know.
What is the note you're using? The reference you're using?
Well, it's the same as Petya used in the first in the first few lectures. So Salomon and the name is Lectures on
I sent it to the channel. It's in here.
Lectures on Floer homology. Okay. Now, this is what happens when we have a single function. Well, when we have a family of functions, we can do the same, and this means we get a family of vector fields. Which we can apply to functions. We know how to apply functions to vector fields, and what do we? No, sorry. There's something. Yeah, something is not quite right. Let me check again. No. This is a vector. This is a vector field which is defined on the whole of M for every t, and we take the value of the vector field at the point x of t, and the result is a vector. It's a tangent vector to what? Well, it's a tangent vector to M at x of t. At small x of t. Well, so is x prime, and so is psi of t. What is this? Well, it's the same as what we denoted here by psi lower t. Okay.
I have a couple of questions. So, if I understood correctly, this x of t is defined by this equation below. So it's okay. And is it obvious that such a vector field exists for every t?
The form omega is non-degenerate. Every linear functional is omega with something. And let's call this something xt. Okay. Now let's see. Well. Let's see what happens when we differentiate. We have two summands, and the differential of the first summand is this, and the differential of the second summand is this. Let's briefly see why. Well, suppose I have a two form on a neighborhood of the unit disk inside C. Now, suppose I do the following thing. Well, I take R close to 1, and I want to consider the integral of the two form eta along the disk of radius r, centered at the origin. And then I differentiate the result with respect to r. What do I get? There is no symplectic manifold, there aren't any loops, nothing. Just a two form on the plane, and I integrate along different disks, and then I want to calculate the derivative. What do I get? Well, I get some integral, but the integral of what? And along what? Differential, sorry, I want to calculate the differential at r equal 1. So the result will probably be the integral along a circle, along the unit circle. Well, this sounds plausible. But the integral of what? Well, d eta is 0 because if we have a two form on the plane, then there aren't any three forms or four forms and so on. Yes, so
I suggest to imagine that eta is constant form.
yes, by the way, all two forms are the constant form times a function.
Yeah, of course, but I suggest to calculate first example when function is 1. dx dy.
Okay, let me write down the answer, and then we'll decide whether or not we want to we want to go into detail. Okay, now the okay, my my claim is the the result is the integral from 0 to 1, and then I want to put the okay the no. I want to put the normal first and the tangent second. Okay, so the answer which I think we get here, but it's well, it's something for everyone to check and criticize. We need to do the following thing. We parameterize the unit circle using 2 pi it, and then for each t from 0 to 1, we apply omega to the normal and the tangent vectors.
What length?
Unit and same for tangent. And we then get a number for every t, and we integrate this this function dt. Well, first of all, does this make any sense? I'm not asking whether or not the answer is correct. Does it make sense? Okay. Now, how to prove or disprove this? Let's see whether or not this this is something completely incomprehensible or something which is sort of clear but not really, or something completely obvious, or something completely obviously false. What sort of statement is this?
Generally, it kind of makes sense. But I mean, I'm not sure about it.
Простите, я забыл, как вас зовут. Как вас зовут?
Лев.
Лев. Какой категории из перечисленных принадлежит вот это утверждение?
Мне кажется, более-менее понятно, как доказывать, только детали нужно время, чтобы понять.
Okay, Saman, is this clear? Sort of clear, not clear at all? Well,
It's technically is good, I mean, I don't understand why, I mean, for me, something is correct or no.
okay, so probably it makes sense to explain this in more detail.
Yeah. And I suggest to consider
Well, Petya suggests to consider the case when eta is dy dx.
even suggest to consider instead of the circle, I suggest to consider a rectangle. Маленькую полоску.
Rectangle. Давай мы вместо полосочки колечко рассмотрим.
Вот. Я советую все-таки полоску.
Полосочку.
Ровная проще, чем круглая. Это моя уверенность, точность, что круг сложнее, чем прямая.
Круг сложнее, чем квадрат.
Да, нет, да, чем прямая.
Okay. Anyway, let's let's think a little. What Petya is saying that instead of the circle, we need to consider a small rectangle. Well,
Or not small.
So suppose we have, for example, a rectangle such that one of the sides is 1.
And second is R.
The other one is R, and
we go with form.
the
Tends to 1.
1 or 0.
1.
Okay, R will okay then.
Square, yeah.
I will go to 1. I will go to 1, and we need to, well, let's call this RR. We need to differentiate we need to differentiate the form, the integral of omega along this
Eta.
eta, yes. Well, by the way, eta will be the pullback of omega, so they're not completely unrelated. Okay, now Well, let's try to remember how to calculate the integral of omega along this. The integral of eta along this this rectangle. Does anyone remember? So this time we have eta, but eta will be some function times dx dy. So this this integral will be let's say that this will be 0, 1, r. So the integral of I integrate from 0 to 1 dx, and then from 0 to r fxy dy. Okay, so now I have something which is probably familiar to everyone. Well, I have this integral, and it's year 1 or year 2, and I want to differentiate this integral with respect to r. Okay, well, suppose f is smooth and continuous on a neighborhood of the rectangle, so all derivatives exist. Now, what happens? Well, so I can interchange integration and differentiation. Well. Okay, what happens when I differentiate this this thing with respect to r? Let me fix an x. And I integrate with respect to y. Then what do I and then differentiate with respect to r? What do I get? Well, something called the Newton-Leibniz formula. What's the answer? Let's forget about x. Let's just look at this integral. And I want to differentiate. X is fixed. I want to differentiate the integral with respect to r. What do I get?
Great.
Okay, so let's let me. Okay, so the answer is I need to integrate f of x of 1 with respect to x. Okay.
It must be integration of f of x and 1 ends, no? Why must it fix here? After taking differential.
Sorry, I didn't.
After taking differential, why must be 1, no? Because they are
Yes.
equal to-
Yes. So why?
Why do you want? Okay, because why I doesn't fit what I say.
Okay, so now let's okay. Well, here what is f of x of 1? Well, what one could say, this is the value of the form that we integrate on at the point t1 on the two basis vectors. One is the unit tangent vector, and the other one is the unit normal vector. This is this example is well, it's too rectangular. So this f blah 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 is the value of the form of the two form on something. Okay, but by the way, does everyone agree with this example? В общем, этот пример слишком прямоугольный. Здесь не очень понятно.
Надо записать инвариантно, перевести его в круг.
Записать вариант. Ну хорошо. Значит,
Сюда поставляется векторное поле как раз,
Нет,
которое нормально. Вот как раз то же самое.
Ну правильно.
Да, все.
Ну, значит, два векторных поля. Одно касательное, другое нормальное.
Да.
Так, значит, вот, yes, there's one other thing, which does everyone remember the change of variables for differential forms? If, well, for example, if I have, anyway, the change of variables. For example, the change of variables is the same as the projection formula. What does this mean? Well, this means, for example, suppose I have a smooth map from Rn to Rn. And I have some submanifold with boundary, and a form I don't know, omega psi eta. Okay, let me call this form omega because it's okay. So the integral of omega along f of v is the same as the integral of the pullback of omega along v. So I can take a form here, integrate along the image. Let's assume that this map is a diffeomorphism. I take omega. By the way, I don't no. I want both. I don't need them. I don't need it to be a diffeomorphism, but I want both blobs to be manifolds with boundary with of the same dimension, so that the integration makes sense. So integrating here is the same as integrating the pullback. Integrating a form along the image is the same as integrating the pullback along something that would take the image off. Anyway, let's look at this example and let's ask ourselves, do we want to so this example is different from this one, but the same sort of argument can be used to prove this this formula. Now, do we want to prove this formula in detail, or shall we say that this example suffices?
I'm not sure how to get from this rectangle to this circle. I mean, explain how to deal with that. Okay.
Ну да, значит, можно взять экспоненты, значит, перевести прямоугольник круг. Можно просто перейти к полярным координатам. Значит, вот,
Начало можно было, конечно.
ну, полярные координаты, они по сути делают то же самое, переводят там прямоугольники в круги и наоборот.
Я бы добавил вот к той формуле, которая снизу написана, что if our form omega is result of, как это по-английски, постановка векторного поля.
Is obtained by substituting a vector field.
Yeah. И
Любой.
где красненький? If we have a map and we have vector field and we take integral, then it equals to yeah. I want to add this.
Okay. Okay, now let's see what this statement has to do with the fact that the differential of the first summand is omega the integral of omega x dot of t psi of t. Well, in our case, the form eta is simply omega pulled back so we have this map U. Well, which is a map from B. Which is a map from V to from B to M. Well, we could we could change this. Well, we could change the map. We could change the map U so that it doesn't matter which U we choose. So let me change the map so that so I have this. I have the map U. Let me suppose that this map is given by my family XS when S is close to close to 0. Meaning when I'm near the unit circle, I have a map which is given by XS, and when I'm far away from the unit circle, I keep the same U as here in the first as in this formula. Okay, now now my claim is that the differential of the first summand will be given by this formula, and this well, here I have the normal which comes first and the tangent which comes later, and here I have the tangent vector which is applied to the first component, and the normal which is applied to the second one. So I get an extra minus. This minus becomes a plus. Okay.
Why do we need to modify the map view?
Because I want to have a single form on the on a neighborhood of the unit disk, and I already have it on the disk, and now.
You just extend it.
I want to extend it, but moreover, I want this. Well, U is a family of maps from the circle to M, and I want this family to coincide with my given family close to the boundary. Okay. Does there is one other thing which I've swept under the carpet here, because when I apply this this functional, I need to have a loop, which is a map from the unit circle to M, and then I need to have a map from the unit disk to M. Now, if I take a disk which is centered at the origin but is slightly bigger than the unit disk, it will no longer be the unit disk. But it's my claim is it doesn't really matter. We basically use the change of variables formula again. The integral of something along a bigger disk is the same as the integral of the same thing is the same as the integral of the pullback of something along a smaller disk. Okay. Let's. I suggest we finish the tangent space today, and then we'll probably need to stop. Let me briefly say something about differentiating the second term. It's this time I have an integral of a function, and we. Okay, let me use another color so that I don't have to erase everything. Okay, so I have I need to differentiate this integral. It's my claim is the result is the integral from 0 to 1 dht applied to psi of t. dht, the differential of ht at the point x naught of t, which is the same as x of t. Well, and then we use we use this well, we use this this formula x of t omega x of t what do we have? Omega x xt psi of t is the same as dh of t applied to psi of t. Okay, so this this follows from the well. Let's forget about x. No, let's not forget about x. Let's take a point. Let's take some point of the manifold. Let's take the value of xt at this point and some tangent vector at the same point. Omega applied to the value of xt and this tangent vector is the same as the differential of dh taken at x at xt applied to the same tangent vector. So here what is important is that everything, the left hand side and the right hand side, everything happens in the tangent space to M at some given point. What is this point? Small x of t. Okay, now I've managed to, well, I've written this, which is okay. I will explain this in a minute if necessary. But let me just use this formula to say that the result is omega xt at xt and psi of t, which is precisely this the second summand of this formula. Now, where does this formula come from? So I have some integral and I want to differentiate it. What do I do? Well, let's see. I want to differentiate. Well, again, everything is smooth. So what I need to do is differentiate this expression with respect to t. Sorry, with respect to s at 0, and then I just integrate and so on. So here I have. I have family of functions, but ht as is clear from the formula, ht does not depend on s. What depends on s? Well, the xs. Okay, so I have some family of functions. Okay. Здесь вот можешь по-простому объяснить, что тут формула, да?
Ряд Тейлора разложить.
Ряд Тейлора. Это как сложно. По-простому, совсем по-простому.
Есть в ряд Тейлора. До первого члена все-таки нам не весь ряд нужен, он большой и страшный.
Так, ну хорошо.
Что такое XS? Это x0 плюс s на что-то маленькое. А дальше не важно.
Так,
Потому что производные нужны.
да. Значит, x0 плюс s умножить на xi плюс, значит, плюс что-то второго порядка.
Да.
Значит, вот, so Petya is saying that this xs is the same as x naught plus, well, here plus
Сам чарт.
yes, вот, да, значит, плюс в каком-то пиковском смысле, потому что, ну,
Конечно.
значит, xs is, okay, psi of t s cross s plus s times psi of t plus etc. terms of higher order. Okay. Well, I think yes, we're sort of run over time. Let's say let's use there is a Monty Python sketch about the best way of getting out of sketches. The best way of getting out of a sketch would be to have a general or a kernel stopping the sketch because it's too silly. So let's stop this lecture and say that this is an exercise. But it's not a massively difficult one. Okay, are there any questions? Comments, remarks, criticism, and so on?
I want to add one
Okay.
line.
Well,
This part is equal to ht in the point at 0 plus s dh of xi plus terms of higher order. So we differentiate it and we get exactly that. It's not a mystery.
it's not a mystery.
Yeah, of course. And we can separate the small charts where we can take plus. здесь. Окей, sorry.
No, no worries. So I think this is it. So let's turn this off.